Okay, so for the second part of the video, I'm going to talk about symmetry and asymptotes and how to find those algebraically. We talked about symmetry the other day in the video, how if it was even symmetry, it was symmetric over the y-axis, and if it was odd symmetry, it had symmetry around the origin. I also had the algebraic part put there, but we never talked about it. So for an even function, if you plug in a number and its opposite, so I'm plugging in x and opposite of x, meaning that could be 2 and -2, -7 and 7, but you plug in a number and its opposite and they equal the same thing, it's even. If you plug in a number and its opposite equals the opposite of what that number did, okay, then it's odd. So if you plug in 2 here and it gives you back 7, let's say it gives you back 7, then you plug in -2 here, it gives you back -7, okay, then it's an odd function. So if opposites give you back the same, it's even. If opposites give you back opposites, it's odd, okay? So same, even, opposite, odd. So you can pick any number you want to plug in as long as it has an opposite. I don't personally necessarily like to plug in -1 or 2. I haven't gone to check if it would possibly work out even if it wasn't even or odd, but I like to choose 2. So I'm just going to do f of 2. So you have to do f of 2 and you have to do the opposite. Okay, so I'm just going to put a little question mark up here and put the opposite over here. So this is just telling me I'm going to plug in 2 for x on this side, -2 on this side, and see if they are the same or opposite. Okay, so I'm just going to write down the function over here. So I'm just going to put x squared plus 3, and over here as well, x squared plus 3. I'm just going to leave it blank because that's where I'm going to plug in the number. Okay, so here I'm going to plug in 2. And here I'm going to plug in -2. So I'm just doing 2 things and we're going to see what happens. So then just evaluate. So 2 squared is 4 plus 3 is 7. So this side is 7. Okay, so we just have to check this side. -2 squared is 4. 4 plus 3 is 7. Okay, so then these were the same number. Okay, opposite inputs gave me the same output, so this function is even, meaning when I look at its graph, okay, it is going to be symmetric around the y-axis. Okay, so let's take a look. Okay, there you go. It's just a quadratic moved up 3 by this plus 3. So symmetric over that y-axis, even. So if you saw the graph, you would know even, and this is how you tell if it's even algebraically. So let's take a look at this one and let's do the same thing. So we're going to take, you can just take 2 again if you want to. So I'm just going to check these ones. So I'm going to check if I plug in 2 and I plug in -2, what happens? Okay, so what's going to happen? So we're going to take the function and I just like to, again, write it down with parentheses where I'm going to plug in the number. So x squared minus 3 times x plus 6 for that side. I'm going to run out of room here. Okay, and then over here, same thing, x squared minus 3 times x plus 6. So we'll plug in 2 over here. And we'll plug in -2 over here, and again, we're going to see what happens. So 2 squared is 4, -3 times 2 is -6, and then plus 6. So 4 minus 6 is -2, plus 6 is +4 for that side. So then let's evaluate at -2. So remember, -2 squared is +4, -2 times -2. -3 times -2 is +6 plus 6. So 4 plus 6 is 10 plus 6 is 16. So these are not equal, so it's not even, and they are not opposites, so it's not odd. So this does not have symmetry around the x-axis, or sorry, around the y-axis or the origin if we look at the graph. So this one was just moved over. It does have an a line of symmetry. It's just not the y-axis. Okay, so this one is neither. So let's look at two more. So again, just taking and plugging in a number and its opposite. So whatever you want to plug in, I'm going to plug in 2 and -2. So then just do this twice. So this will be 2x cubed minus 2 times x plus 1. And then we're going to see what happens when we plug in -2. Okay, so plug in 2 and then plug in -2 and evaluate. So 2 squared is 4, -2 times 2 is -4 plus 1. So 4 minus 4 is 0, plus 1 is 1. Next one, 2 squared, -2 squared is 4, -2 times -2 is +4, plus 1. So 4 plus 4 is 8, plus 1 is 9. So these are not equal and they're not opposites. So this is neither even nor odd. Oops. Okay, so we can delete that and take a look. So not symmetric around the y-axis and also not symmetric around the origin. And then final example on how to do symmetry algebraically, we'll do into this function. So we'll plug in 2 again and plug in -2. So this function is x cubed minus 2 times x. So we'll do that for each one. Plugging in 2 on the left and then -2 on the right and just checking for equal or opposite. So 2 cubed is 8. -2 times, whoopsies. -2 times 2 is -4. And then 8 minus 4 is 4. Over here, -2 cubed is -8. -2 times -2 is +4. Add those together and you get -4. So now we have opposites. So 4 and -4 are opposites of each other. Opposites means it's an odd function, which graphically speaking is going to mean that it's symmetric around the origin. So this one goes through the origin. I could rotate it 180 degrees right around the origin and it would flip right back on itself. So odd function. All right, then we're going to get into asymptotes. So you're going to want to pause each screen and definitely write down the definitions here. And then listen as I talk about it and add some more information. So a horizontal asymptote is just a horizontal line, so a y equals line, y equals any number, in this case I'm calling it b, is a horizontal asymptote of the graph if your function, okay, so whatever your function is, approaches that line at its ends, okay, at infinity and negative infinity. So, you know, negative infinity is way out here. So it needs to be getting closer and closer to this line as we go to negative infinity. Okay, and then on the right-hand side, it also needs to be getting closer and closer to this line as we get closer and closer to positive infinity. So if you were to plug in like 1 million into this function, it would pretty much give you b. If you were to plug in -1 million into this function, it would pretty much give you back b. So at the ends, it needs to be approaching b. This is limit notation. Okay, so this is our introduction to writing in limit notation. We will use this more as the year goes on, but this is read the limit as x approaches negative infinity. So as we're going to the left side of the graph, so as your x's are getting like more and more negative, -1, -10, -100, -1,000, -1,000,000, they're getting closer and closer to negative infinity, the function is approaching this number, whatever it is. So this is really talking about the left side of the graph. Okay, then the limit as x approaches positive infinity, so 1, 10, 100, 1,000, 1,000,000. So as your graph on the right side of your graph, okay, as your x's are getting bigger and bigger to the right, this function is also approaching this number. Okay, so it's going towards b. Then that's a horizontal asymptote. Okay, so for horizontal asymptotes, you've talked about these in Algebra 2, how to find them. They're the end behavior, okay? They're like the end behavior of your graph. So remember, if you have any polynomial function, so this is just the leading term, okay? So you could have like x cubed, you could have like 5x cubed plus 3x squared minus 5x, whatever, okay? I'm just writing down just the leading coefficient, okay? This is just the leading coefficient. So if the degree on top is larger than the bottom, so if you have an x cubed over an x squared, okay, so if the degree on top is bigger than the bottom, there is no horizontal asymptote. If the degree on bottom is larger, so if we have x squared over x cubed, so if n is greater than m, then the horizontal asymptote is automatically y equals 0. If they're the same, you have an x cubed over an x cubed, an x to the fifth over an x to the fifth, then your horizontal asymptote is the ratio of these lead coefficients. So if you had a 3x squared over a 5x squared, the horizontal asymptote would be y equals 3/5. Okay, just the ratio of those if your degrees are the same. When we're talking vertical asymptotes, okay, so again, you can pause this, write this down. A vertical asymptote is a vertical line, so an x equals line. So x equals this number, whatever it happens to be, is a vertical asymptote if the graph of the function, okay, so if your function is approaching positive infinity or negative infinity when it gets closer to a. Okay, so on either side of A, the graph is getting really close to it. Okay, so you see this, it's getting close and it's going towards infinity or negative infinity, either one. Okay, so the vertical asymptote goes towards infinity. So as we get closer to A, so let's say this number is 2. If your table is 2.01, you're really close, okay, to infinity. Okay, your output is really big. If you're 2.001, 2.0001, as you get closer and closer to this number, your output is getting bigger and bigger and bigger. Let's say it's 100, 1,000, okay, 10,000, whatever. This number is getting larger and larger. Or in this side, okay, maybe it's 1.9, 1.99. As you're getting closer and closer to A from the left-hand side, again, this output is either getting really big if it's going to positive infinity or really big negative if it's going to negative infinity. So maybe it's negative 100, negative 1,000, negative 10,000 or 1,000,000 or whatever. This just keeps, as this number gets closer to here, the output gets more and more negative. Okay, so the limit notation, the limit as x approaches A from the positive side. Okay, so you see how this is like an exponent almost? This means as it approaches A from the right, meaning the numbers are bigger than A. So like I said, if this is 2, then they're like 2.01 or 2.001. They're getting really, really close. So it'd be like if you plugged in 10, 9, 8, 7, 6, 5, 4, 3, 2, well, not 2, you're not going to plug in 2, but 2.5, 2.4, 2.3. Okay, it's just going to get closer and closer here. Then the limit as x approaches A from the left, so this negative sign means that you're looking at the left side of A. So the numbers over here as x gets closer and closer to A from the left. -3, -2, -1, 0, 1, 1.5, 1.9, 1.99, 1.999. As they get closer and closer to A from the left, your graph is going to either, or your outputs are going to either positive or negative infinity. That's the definition of a vertical asymptote. Vertical asymptotes are, sorry, I didn't mention this, are where the denominator equals 0. So when you have a denominator, vertical asymptotes come from the denominator. So let's take a look at two of these. So let's determine the asymptotes here. So let's do the horizontal asymptote first. That has to do with the degree on top and the degree on bottom, okay? Your horizontal asymptotes are a y equals line. You need to write that. So you need to put, this is a line. It's not just a number. You can't just tell me 3. You need to tell me y equals 3. So take a look. The degree on top is 1. The degree on bottom is 1. They are the same. So we will divide the coefficients there. 3 divided by 1. So your horizontal asymptote in this one is the line y equals 3. Vertical asymptote is when the denominator equals 0. So in this case, our denominator, okay, is x plus 1. So when that equals 0, it will give us our vertical asymptote. So subtract 1 from both sides, and your vertical asymptote is x equals negative 1. Let's take a look at the graph to confirm. So if we take a look here, let me get a line. Okay, our horizontal asymptote right here, y equals 3. As the graph goes to the left, it's going towards 3. As the graph goes to the right, it's going towards y equals 3. So y equals 3 is our horizontal. Our vertical, right here, x equals negative 1. As we come at negative 1 from the left, the graph goes up. So on the left side of negative 1, the graph is up here at infinity. When we come at it from the right, the graph is down here at negative infinity. Okay, last example on asymptotes, horizontal asymptote, again with the degree. So check the degree on top is 1. Okay, the degree on bottom is also 1. So divide the coefficients, 1 and negative 2. So y equals 1 divided by negative 2, or negative 1/2. Okay, so there's your horizontal asymptote. Vertical asymptote, again, is where the denominator equals 0. So the denominator is 4 minus 2x. If there isn't a denominator or it can't equal 0, then you would have no vertical asymptote. Okay, so 4 minus 2x equals 0. So we can subtract 4 from both sides. Divide by negative 2. So negative 4 divided by negative 2 is positive 2. And that's your vertical asymptote. So let's take a look at the graph to confirm. Okay, so horizontal asymptote we said was negative 1/2. So we can see that line in there, negative 1/2. And then vertical asymptote we got was x equals 2. So if you divided wrong and accidentally got negative 2, graphing it's going to help you if you thought it was negative 2. Okay, so then you can see on the graph that it's positive 2. All right, then let's do a final analysis of this function that we brought into play in our videos, in our first videos for this way back when. So the function here, remember, was a quartic because it's an x to the 4th polynomial. That's what that's called. Domain, we've got an arrow to the left, an arrow to the right. So all real numbers in interval notation is negative infinity to infinity. Range, okay, it's bounded below here. There's a bottom number that it can't go past. So I'm going to actually put that in. It's bounded here at y equals negative 24.057, and it's bounded below. So that means our range starts at that number. We do have a point there, so it's going to be a hard bracket, and then up to infinity. We can draw this whole function with one pencil motion without lifting up our pencil. So there's no discontinuity. So I'm just going to put a dash through there. What intervals is it increasing on? Okay, so increasing, so it's from the maxes and mins, okay, so we've got a minimum here. Our function is going to increase here. Okay, remember we want to name the x intervals. Okay, so it's increasing from this x to this x. So the increasing interval is negative 2.057 up to 0.456. It is decreasing here. Okay, so this x value here is negative infinity. It's going to decrease until this x value. Okay, so it's decreasing on this interval, negative 2.057 again. Okay, so decreasing from negative infinity to negative 2.057. Also decreasing from here to here. So this x value 0.456 to this x value 1.601. Okay, and then I missed an increasing interval. So it increases from here onward. So from this x value to positive infinity. So I'm just going to add that in over here from 1.601 up to infinity for that increasing. Okay, asymptotes, there are none. Okay, there's no vertical asymptotes. The graph isn't going towards any number at the ends. It's going to infinity, so no horizontal. Symmetry, none. Maximums, there's one. That's 0.456, 1.324. And then there are two minimums, negative 2.057, negative 24.057. And then the 1.601, negative 1.76, whoops, 0.766. Get me out of there. Okay, then you can see we've got those two, this minimum and this minimum, and then a max here. So that's doing a full analysis of a function, so you should be able to do that for all functions now.